I want to go through an example where we apply two different equations of state to the same substance to see what the differences are. So in this case, I'm taking the van der Waals equation of state, outlined in your lecture notes, and the ideal gas equation of state, which we've used many times, and we're going to apply it to water. So specifically, we're thinking water at a temperature of 400 Kelvin and a specific volume of 0.820 cubic meters per kilogram. What I want to do is I want to use the two different equations of state to compute the pressure for the water under these conditions and just see how much the pressure varies between the two different equations of state. So the ideal gas law tells us that we can get the pressure from PV equals RT. The van der Waals equation of state tells us that the pressure is this kind of complicated looking arrangement of R bar temperature, V bar, and then these two constants A and B that are associated specifically with the van der Waals equation of state. You can look them up in your book in table 824, and we'll do that in a minute. But first, let's see what answer we get with the ideal gas law. So P little v equals RT. We can rearrange that to solve for pressure. You can always rewrite R as R bar over M. And now we can just plug in values, right? R bar is 8314 joules per kilomole Kelvin. The temperature was 400 Kelvin. Big M for water is 18.02 kilograms per kilomole. That's molecular weight. And then little v is 0.820 cubic meters per kilogram. Multiply all that together, you get that P is 2.251 times 10 to the 5th pascals. Or if you want to work in bar, it's 2.251 bar. I'm going to assume that we have four significant digits so that we can compare with some accuracy between van der Waals and ideal gas equations of state. Okay, so we'll write 2.251 bar up near the ideal gas law to remember that was our result and erase all this. Now we're going to use the van der Waals equation of state. Okay, so it looks like that. Well, first let's translate between V and V bar because we're given little v. So V bar is just big M, the molecular weight, times little v. Remember, this is how you go between barred quantities and unbarred quantities, just as we've done many times with R bar and regular R. So we can substitute that into the equation of state. All right. Now we know all the rest of this stuff except for the values of A and B, which we have to look up. So you go to table A24 in the back of your textbook, and it has it listed for different substances, but it's constant for a given substance, which is nice. So in this case, A is 5.531. It's weird units, bars times cubic meters per kilomole quantity squared. Okay, that's A. B is in also weird units of 0.0305 cubic meters per kilomole. So ultimately, we're going to have to make sure that we check our units carefully when we apply this equation of state. Honestly, that's the toughest part about using the van der Waals equation of state. If you want to cross-compare with something else or make sure that you have sensible units, just making sure that you handle A and B correctly. So let's plug everything in, and when we do that, we can see, okay, in the first term, we plugged in all of our values, and the only different value now is that value of B we had to look up. So in the denominator of the first term, the value of B is in units of cubic meters per kilomole, but actually it's being subtracted away from big M times little v, which will also have units of cubic meters per kilomole, and we can see that kilomole is going to cancel with the kilomole that was in R bar, so actually those units will be fine. When we multiply out that entire first term, it should give us units of pascals. What about the second term? Well, the second term, obviously we're going to end up getting units of bar, because bar was in the unit of A, and then you can see that all the other stuff is going to cancel out, right? We have a cubic meters per kilomole quantity squared in the numerator, but then we're going to get the same thing in the denominator, so we'll be left in bar. If we want to add these two terms, we probably want to make sure to work either in pascals or bars. I'm actually going to convert the first term into bar, which we can do by dividing by 10 to the 5th, right? Because I'll put the conversion factor in. 1 bar equals 10 to the 5th pascals, so now that means our first term and our second term will come out in bar, which also helps us compare with the result from the ideal gas law. Okay, so let's simplify these terms. We multiply things out. First term becomes 2.25527 bar, and then you can see the second term is a very small correction, 0.02533 bar. All right, add those together and we get a result that is 2.230 bar. So that's our final result using the van der Waals equation of state. I'll put that up there. You can see that the two numbers are very similar, but they differ by about 1%, a little bit less than 1%. Now, the interesting thing is we actually don't know which one is correct. We don't know that either is correct. Really what we would have to do is either do an experiment very carefully, determine the values, and then see which of these two equations of state applied more directly, or you can imagine consulting a compressibility chart to see how applicable the ideal gas law should be. You can imagine applying other equations of state, seeing what sort of convergence you get. The bottom line is, we know the answer pretty well, certainly to 2 significant digits, and almost to 3, But that's about the level at which we can rely on these results. Otherwise, you have to really investigate the validity of your equation of state before assuming that you have like 5 or 10 significant digits on these results.